presentation, we'll go over molecular orbital theory. Our objectives will outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals. We'll describe the traits of bonding and antibonding orbitals, and we'll calculate bond orders based on the molecular electron configurations. Let's go over the basic assumptions of molecular orbital theory. The number of molecular orbitals equals the number of atomic orbitals used to create them. So this is analogous to valence bond theory, where the number of atomic orbitals was equal to the number of hybrid orbitals. 2. Atomic orbitals with similar energy and shape, same n and l principal quantum number and angular momentum quantum number, mix more effectively than those that have different energies and shapes. So let's expound upon this a little bit and give some examples. An s orbital combined with another s orbital will mix better than an s orbital and a p orbital. A 1s orbital from hydrogen will bond better with a 2s orbital from carbon than it will a 3s orbital from silicon. A 2s orbital from carbon will bond very well with another 2s from carbon, but not as well between a 2s from carbon and a 2p from carbon. Hopefully that gives you an idea what we're talking about. Our third point, atomic orbitals have different principal quantum numbers. Atomic orbitals of different principal quantum numbers, n, have different sizes and energies, resulting in less effective mixing. So better mixing leads to larger energy difference between the bonding and antibonding orbitals, and thus greater stabilization of the bonding molecular orbitals. And I know bonding and antibonding does not make sense right now, but it will in the remaining slides. So when you get to the end of this presentation, you may want to come back to these points and revisit them with the new pictures in your head. Anyway, what to take away from this point right now? Better mixing equals more stability, and better mixing equals larger energy differences. Point 4. A molecular orbital can accommodate a maximum of 2 electrons. 2 electrons in the same molecular orbital have opposite spins because it still follows the Pauli exclusion principle. It's just applied in this context. And finally, number 5, electrons occupy the lowest energy molecular orbital available following Hund's rule. So again, we're still using the orbital filling rules within this new context. Now that we have the basic assumptions, let's take a look at these suckers. When we combine orbitals from 2 different atoms, we are still using a linear combination of atomic orbitals. But because we're using different assumptions than with valence bond theory, we'll get different results. Our basic assumption with molecular orbital theory is that we're combining the orbitals of different atoms. With valence bond theory, we combined orbitals of the central atom only. I want to call that difference out early. When we combine orbitals from 2 different atoms, we get a molecular orbital with a delocalized charge. If the 2 orbitals have electrons, they're waves, right? Wave, particle, both at the same time. If they're in phase, they make a bonding orbital and have a lower overall energy. Higher amplitude, lower energy. Then the antibonding orbitals. So the antibonding orbitals will form a node. They'll cancel each other out. They subtract. Their electrons are going to be in 2 different places. If you take a look at the picture of the molecular orbitals, so we start out with 2 spheres. Note they have dots in the center. These are from 2 different atoms. We put them together. When they add, they overlap in space. That's why we call them bonding orbitals. When they add, they overlap along the internuclear axis. When they subtract, we get a node on the perpendicular to the internuclear axis where we have no electron density. It is the opposite of bonding, right? When we don't have an overlap, it's not bonding. So that's where the names came from. The overlap of the electron density is why the in-phase version is called bonding and why the out-of-phase version is called antibonding. After all, bonds overlap electron density, and the electrons in the bonding orbital are attracted to both nuclei, while the electrons in the antibonding orbital are attracted to one nuclei at a time. Bonding orbitals are called sigma or pi. Sigma, designated by lowercase Greek sigma, and then subscript s if they come from s orbitals, and antibonding orbitals are given by sigma dash s star. We don't actually say the dash s. So sigma s star is that designation. Sorry, I'll point it out with the laser pointer. right there. Boom. Okay, so what happens when we combine p orbitals? Let's look at that next. P orbitals can be oriented along the x-axis, the y-axis, or the z-axis, or z-axis. Prefer. They have two areas of electron density, and those are different phases. We color code those phases. So when two orbitals of the same phase come together, we get a bonding orbital, and we designate it as sigma because the overlap is along the bonding axis. We give it P, right? We have sigma, overlap along internuclear axis, a P because that's what we mixed to make the orbital, and an X because that is, again, what we mixed. We mixed PX orbitals together. The antibonding version has electron density falling outside of the internuclear axis for the most part. There's a node perpendicular here. We give it a sigma px, because again it's coming from px orbitals, star. The star meaning antibonding. There are 3 nodes in this sucker. 1, 2, 3. All right. Now that we know what it looks like when we overlap px orbitals, what else can we do? I would like you to predict what will happen when 2 p orbitals combine, when they're vertically aligned and parallel to each other, just like in those pi bonds that we've talked about before. What do the bonding and antibonding orbitals look like? Pause here, try to puzzle through what this might look like, and we'll have the answer soon. In both the bonding and antibonding cases, we have a nodal playing along the internuclear axis. Boop. Right there. There is an additional node that's going to bisect the internuclear axis of the antibonding orbital. Hopefully you got that point, where the electrons generally were. This slightly slanted shape would be hard to predict without knowledge that that's what it looks like. That's cool. Just know it for now. So, note that we have changed the designations. So instead of having a sigma, like we did on the previous slide, we have a pi. Pi meaning this is how they combine with that node along the internuclear axis. Pi p indicates that it's bonding, and pi p star indicates that it's antibonding. So let's talk about these designations in general. We give the type of bond, sigma or pi, aligned along the internuclear axis for sigma, containing a node along the internuclear axis for pi, followed by a subscript, which indicates the orbital that it was combined from and the axis that it was aligned along. So, additionally, when you have the same colors for your nodes, they're the same phase, and that's where you get the additive bonding phase. When they have opposite colors, they're different phases and they subtract. And this red-blue designation, this color scheme, it's totally arbitrary, but that's the standard one that we use, red versus blue. By convention, we designate the sigma bond as being along the x-axis for our p orbital overlap, and the pi bonds as being along the y or z. So pi orbitals are degenerate with each other. We have the 3 of them coming from both different atoms. When we combine them, we can make 6 different combinations, because remember, number of orbitals in equals number of orbitals out. These are given by sigma px star, pi py star, pi pz, and pi pz star. Pi py and pi pz are degenerate. Pi py star and pz star are also degenerate. So we have 3 orbitals from each atom going in, 6 orbitals coming out, as we were supposed to. As a final note, we cannot align 2 orbitals with wrong orientation together. A px and a pz will not make an orbital. It will not mix. The electron densities will cancel each other out. And the valence bond theory, we talked about hybrid orbitals alongside the shape. This time, we've separated that concept. So hybrid orbital diagrams alongside the shape. We are not doing molecular orbital diagrams alongside the shape. The reason for that is we're working with two different types of diagram. The hybrid orbitals, we were familiar with that type of thing. We'll have two sets of atomic orbitals and we'll combine them into one set of molecular orbitals, and that'll be in another presentation for this concept. All right, let's summarize. Molecular orbitals are linear combinations of atomic orbitals made from atomic orbitals on two different nuclei. They have delocalized charge. Molecular orbitals have bonding and antibonding orbitals. The bonding orbitals have lower energy than the original orbitals that they're made from, and the antibonding orbitals are the highest energy in this scenario, so they're higher than the bonding and they're higher than the original orbitals. Molecular orbitals are designated by the type of bond, sigma, given by lowercase Greek sigma, or pi, given by lowercase Greek pi, and a subscript indicating the contributing orbital, including the direction, and then followed by a star if it's an antibonding orbital. So for example, we have sigma s star and sigma px as an antibonding and a bonding case.